Okay, for tutorial 8, mass transfer in bubble column. Bubble columns are used for liquid aeration and gas-liquid reactions. Thus, finely suspended bubbles produce large interfacial areas for effective mass transfer, where the contact area per unit volume of emulsion is calculated from the expression of such, where epsilon is the um, volume fraction of the injected gas. While simple to design and construct, bubble columns sustain rather large eddy dispersion coefficients, and this must be accounted for in the modeling process. For concurrent operation, liquid of superficial velocity is injected in parallel with gas of superficial velocity UOG. The liquid velocity profile can be taken as plug shape, and the gas voidage can be treated as uniform throughout the column. We wish to model a column used to aerate water, such that the liquid enters with the composition CO. Axial dispersion can be modeled using a Ficken-like relationship as such. While the solubility of dissolved oxygen is denoted as C star, we shall denote distance from the bottom of the column as x. Now A, derive the steady-state oxygen mole balance for an incremental volume of this, A being the column cross-sectional area, and show that the liquid phase balance is this. Lump parameters by defining a new dimensionless length as this, and define the excess concentration as y equals to C minus C star, and so obtain the elementary second-order ordinary differential equation 4, where equation A equals to this. Note the usual condition in practice are such that A is less than 1. And for part C, perform a material balance at the entrance of the column as follows. Far upstream, the transport of solute is mainly by convection, and the column entrance x equals to 0. Two modes of transport are present, hence show that one of the boundary conditions should be this, and the second necessary boundary condition is usually taken to be this, where L denotes the position of the liquid exit. What is the physical meaning of this condition? The two boundary conditions are often referred as Danckwerts type in order of PV Danckwerts. Okay. So for part A, um, this is what it looks like. Okay. So you have your liquid and your bubble being aerated. So first we will have the steady state material balance for dissolved oxygen, which is we are balancing for the liquid phase, which is this equation. Okay. So the first part over here is your convection, and this part is your diffusion, right? Then we can divide the equation by A delta X, which leaves us, okay, and we can also take the limit as delta X approaches 0, and we will get our final equation as negative UOL dc over dx minus 1 minus epsilon dj over dx plus kCa c star minus c equals to 0. Okay? Now, we substitute j, with negative dc over dx. Okay? That means we would get negative UOL dc dx minus 1 minus epsilon, and substitute your j with significant negative dc plus kca c star minus c equals to 0. And therefore, this one would become, this one is minus. So we can lump these two together, which gives us negative UOL dc dx minus 1. So this one you have a negative, so this one becomes plus. This one is 1 minus epsilon and dc. Okay, in the question is supposed to be dc or de. de, sorry, this one is de. Okay, de. de and d square c over dx square plus kc, okay, same thing, minus c equals to 0. Okay, then we can put the positive part to the front, and this is your profile. Now for part B, we want to lump the parameter by defining a new dimensionless length, which is your z is given to be k cax over uol. Okay, so for here we can do dz dx is equals to kca. Okay, you have a over here, the rest are constant, kca over uol. Therefore dz is equals to kca over uol dx. And we can take y to be equal to c minus c star, whereby dy is over dc is equals to 1. Okay, 1 over here. Therefore, dy is equals to dc. In this case, from the equation above, from part A, 1 minus epsilon dc, we break this one down, becomes ddx over ddc over dx minus uol dc dx plus kc a c minus c equals to 0. Okay, so this part here is equal to dz over dx multiplied by d over dz. What does this mean? dc, so this one is dz over dx. Okay, we can take this multiplied by d over dz. Dz. So when you cross this, you get the same thing back, dx over here. Multiply by same goes with dc, so it's dc over dy. Multiply by dy dz. Multiply by dz dx. Okay, minus uol. So dc dx, same thing, is same as here. So you get dc dx. So dz is cancelled off, dy is cancelled off over here. So it's the same thing over here, dc dy multiplied by dy dz multiplied by dz dx minus k c a y. So we already replace your y with replace your c star minus c with your y, which is equals to 0. Okay, now then we can substitute everything in, which gives us this a little bit. Okay, so we get 1 minus epsilon dc. So this one is kc a over uol, right? The one that we derived, multiplied by d dz multiplied by, so this is equal to 1, okay, and this one will keep, and this one is kca over uol. So this is 1 multiplied by dy dz kca uol minus uol bracket dc, same thing, 1 multiplied by dy dz multiplied by kca uol minus kcay equals to 0. Equals to 0 over here. Okay, then we can summarize everything. We can simplify the equation. So this one is taken out, okay, because it's a constant and it's not a function of anything here. So we should get 1 minus e dc kc square a square over uol square, okay, and bracket this 2 d square y over d z square minus, so your ul is cancelled off over here, so we get kca dy dz. Okay, and then it should be minus with k c a y equals to 0. Then we divide everything by k c and a. Therefore, we should get 1 minus epsilon d dE, sorry, this is dE, I kept pronouncing it as dc, okay, kca, okay, d square y divided by minus dy dz minus y is equals to 0. Alright, so that's for your part B. Okay, so for part C, perform a material balance at the entrance. Let me show you how it looks like. Okay, okay, never mind about that. So the question says that perform a material balance at the entrance to the column as follows. For the upstream, the transport of solution mainly by convection. Okay, so for the upstream, only convection is available. Okay, meaning at the entrance. At the column entrance where x equals to 0, two modes of transport are present. Okay, so this is your entrance part at x equals to 0. So at the entrance, there's two modes. Okay, one is your one is your convection, and another one is your diffusion. Right. So let's say this one is your j, x equals to 0. This one is your UOL at 0, at x equals to 0. Okay, so we will do the material balance at the entrance of the column, whereby it should look like this. A UOL CO minus, okay, the exit over here, A UOL C at x equals to 0 minus A 1 minus epsilon J at x equals to 0 gives you 0. So we divide everything by A, okay, we get UOL CO minus UOL C at x equals to 0 minus 1 minus epsilon J at x equals to 0 equals to 0. Next. Okay. Then we can move the equation around, okay, and substitute your J with dC, dE, and multiply by dC over dx. So we will get so we move this 2 over to the right hand side. UOL C at x equals to 0 minus 1 minus epsilon, and this is your dE dC dx at x equals to 0. Okay, sorry, this one is negative over here. J is equals to negative dE, and this, then that should gives us with C at x equals to 0 plus 1 minus epsilon, because your negative over here multiplied with your negative over here, this. And the second boundary condition should be dC over dx equals to 0 at x equals to L. Okay, so at the exit of the column, there is no net flux of the dissolved oxygen, that is at the end of the column. The concentration of the dissolved oxygen is constant with respect to the axial position because the liquid phase ends there, which is at the top of the interface. So that's all for tutorial 8.